Okay, welcome everyone. I hope you enjoyed and found the food. So welcome to the first seminar of the seminar series that we'll be hosting at the Complex Systems Center this year, which is on tipping behavior in natural and societal systems. So today, Robbin will kick off the seminar and the seminar series, and each month we'll have one of the seminars in the system in the series, and outside of that there will also be some other activities. So keep a look on the website to see what's going on. But for now, we're very happy to have Robbin Bastiaansen kick off. He's an assistant professor at both IMAU and the Department of Mathematics, researching tipping points. And that's the information you're going to get.
Thanks, Linda. Yeah, as Linda said, I work half of my time at the mathematics department, half of my time at the physics department. So when I talk about tipping, I typically think in the context of ecosystems, climate systems, and things that have to do with natural systems and how they behave. But what I planned for this talk is to give a lot of examples from all different fields. So let me ask you, what sort of fields are you from? So who wants to say? I think someone could. Yeah,
Economics.
Economics, very good. Other economics? Yeah, all right. Biology, I saw some people as well, I suppose. Other fields? Sorry?
Biophysics.
Biophysics. Other fields as well?
Human geography.
Human. Okay, all right.
All
All right. So what I will say, I will touch up on some of these systems. I probably will mess up the details. If you think so, perhaps later in the series you might want to give us the actual explanation for that. So I plan to do the general introduction of what tipping points are, and then later on, if I have time, I have a few examples of more complicated or more complex systems, still relatively easy, mathematically speaking, to show that in complex systems, things are a bit more nuanced and a bit more complex than what I will tell in the first part. And I'll see how far along I get in this. So I thought if you talk about something and try to introduce it, you need some definition. And I find it very hard to find a definition that everybody agrees with. So I think the most quoted would be the definition that IPCC made. And that says that tipping points are a critical threshold beyond which the system reorganizes, often abruptly and or irreversibly. And I will touch upon most of what is being said here. But I thought, actually, if I start to talk about tipping points, it might be nice to show an actual tipping point that you might recognize. Right? So, if you have a seesaw like this, what happens if there's more weight here? This goes down. If there's more weight here, this goes down. So you have a tipping between a state where this side is down and where this side is down. And that sort of idea that you have transitions from one state to another, depending on what sort of forces your system experienced, that is what you can think of as a tipping point. So I thought, well, here's a drawing for the same situation. But I thought, well, if you have this idea, by saying putting more weight on the right or on the left, and having different kind of outcomes, there might be some other systems that behave like this, and some other systems where you see something that you could see as showcasing tipping. So, for instance, if you have some sort of election going on, there might be very different outcomes depending on how most of the votes are being done. So here you have the same kind of transition depending on more votes to the right or to the left. And you have this in a very large amount of systems. So, so I try to put some nice visuals in here. So what you can think of is a situation where you have new innovations trying to come to the market. And then what you see there is that typically at the start of it, there's only a few people who try to pick up such new technology. And then you get people making cartoons like this. And I forgot when this is from, very long ago. When people were talking about mobile phones, and it was ridiculized in cartoons, saying basically, we don't need phones. But then later on, if there's a critical mass, enough people that have adapt to this, then at some point, relatively fast, this takes over our society, as you now have like little children constantly playing on their phones. You have this in other systems, in financial systems, you might have something similar happening. So I try to put on some nice visuals and a quote that is not completely readable. Okay, anything. So this is a quote that typically is cited in this context of tipping points. And this comes from a novel by Hemingway, where somewhere in there, somebody went bankrupt and he's being questioned, how did it happen? And what he said is, well, two ways. First, gradually, and then suddenly. And with that, he meant he made some small mistakes on small mismanagement of his finances. And then there was some slow things happening. And then suddenly there was enough of these small mistakes, and then things went downhill very fast. And that's a signature that you typically see with tipping. You can have very small forces do hardly anything, and then suddenly there's this critical mass, there's too much of this forcing, and suddenly you see a shift in your system. And this idea, especially from these more social examples, sort of accumulated, I would say, in a book that was published around 2000 called The Tipping Point. And I think this is where the term tipping points actually originated. And in this book is all what I've said before with this critical mass and how small changes could accumulate in society is explained there. And then this term tipping points was introduced. However, if you then give a talk about tipping points to especially mathematicians, they will say, well, you say this is 2000s and perhaps more recent, but if you go back into the mathematical literature, you see people doing this almost 100 years ago already. So for those people, and I don't think too many of you are in the room today, I added a few slides, starting with this one. So who does recognize this? Sorry? Thanks. I forgot who it was. Yeah. So what he did in his paintings typically, especially in his later work, is try to incorporate a lot of science. And one of his last paintings is this paintings of a very particular illustration of a bifurcation occurring in a dynamical system. And this is then what people talk about. To me, if I give a talk about tipping points to mathematicians, they say, well, there was something called catastrophe theory. Basically, that studies structural changes to something called the potential function or an energy function or a Lyapunov function of something. And then they make drawings of this potential landscape, and then they say there might be faults in that landscape. And then how you should read this is that on top of this here, there is a certain state, and I think this is for panic. No clue of the context here. But say here, you're in a panic state, and then your environmental conditions, whatever that may be in that context, change. You follow this landscape, and then you arrive at a fault. And if you arrive at that fault, you fall down and you come in a calmness state. So that is then how you could explain tipping points. And if you now look in the literature, you will see an argument very much like that, where people make a drawing of a potential landscape that indicates the stability. So I made this drawing a few years back when I tried to explain this to 7-8-year-old children. So I thought it might fit for this audience as well.
Thank you.
Let's see if I can pull out. Sorry. So what you should see here is on the horizontal axis is a representation of your state of your system. And on the vertical axis should be how the energy landscape looks like. And then we should imagine that this landscape is just an actual landscape. And if you start somewhere here, you roll downwards into one of these valleys. So I've represented that with a ball. And then because there might be external forces, this landscape can change. So perhaps over time, something like this happens. And the ball is still roughly in the same state, but the valley is less shallow. But what has happened is that another valley has appeared here. However, nothing has happened yet. But if things keep on changing, at some point, it could happen that this valley completely disappears there. And then what you will see, with the power of very bad PowerPoint animation, is that it rolls to a completely different state. So this is also how people explain tipping points. And then the idea is you can go back to the other state, but you have to do a lot of work, basically, fully removing this alternative state. And then, only then, you fall back. So this is how typically tipping is explained with this mental image. There are some reasons that this does not apply to all systems. Won't touch on that too much. But with this idea in mind, a lot of people, especially in biology and ecology, thought, well, this idea we could use to explain critical shifts in our systems. So one of the earliest things people found is that in small lakes, there is a shift between a very clear lake and a very turbid lake that is associated to the amount of nutrients that you put into your lake. So I asked that some people might have small ponds. There you might see that if you overfeed your fish, then suddenly overnight it can turn from a clear pond to a very turbid pond. And then making it clear again is very hard work, typically. And after finding that in these small lakes, people have also found it in other systems. So for instance, you might have shifts between full ecosystems. So for instance, rainforest to savanna, back and forth could be transitions there. So all of these kind of things. And if you're more interested in some graphs, I have one here, and for a while, only one, where you would see a time series, so time going to the right, and here's some representation of your state, and then a tipping point would be like fluctuations around one mean state, and then suddenly jumping to another. So that's all representations of critical shifts or tipping happening. And then later on, people have also thought about these shifts happening on a planetary scale. So for instance, between an Earth with a lot of ice and an Earth without a lot of ice. So ice ages could be explained by this phenomena of transitioning between different states, depending on, in this case, the solar forcing. So if you want to look into the literature, especially around ecosystems, you would go to Hulling, Neumeier, and May in the 1970s. So that precedes this tipping point thinking of the last 20-ish years by it. So it brings me back to this definition of the IPCC, where they talked about a critical threshold. And that's what we have seen now. There might be a critical mass or a critical forcing of the sun, all that sort of things. Or as a critical threshold, then suddenly your system can change to a different state. So that is the abruptly as well. And the irreversibly is because typically it takes a lot of effort to go back to the previous state. And sometimes it's not possible at all. So I also want to highlight a few climate examples, because there is a nice map that I can show you. This is a map of 3 years ago, where they made a review of all the larger climate elements that might show this tipping behavior, so these critical shifts between different states. And in there you have ocean circulation, you have the rainforest again, you have coral reefs, some things with ice, a lot of things. Let's do this for a bit. So for instance, there, if you want to study ice sheets, people have done some experiments in models. There they find images that look like this, where you put on the horizontal axis some sort of forcing of your system, and on the vertical axis some representation of the state of your system. And in this case, what they found, perhaps it's easier to see here, is if they put on forcing, you will follow this black line more or less. And then around here is what they have found is a tipping point. You go from here relatively fast to another state. And then here, yet again, to another state. And then if you want to go back, you really have to put in more work. Then you have to go to here to go back up, and to here to go back up yet again. So there is some hysteresis in there as well. And this idea of tipping happens in other systems as well. And I try to find nice figures for a lot of other systems, but that's very hard. So I asked Gemini to make some images for power grids, for ocean circulation, and for brain dynamics. Those are very bad on the science level, but they look nice, right? So they don't make sense. But in all of these systems, people are using techniques associated with tipping to explain the phenomena happening there. So in power grids, it could be the blackouts that might happen there. In ocean circulation, it could be what happens when an ocean circulation suddenly changes to something else. And in brain dynamics, people are thinking, for instance, about migraines, how they appear. So that's a bit of the introduction of all sort of systems where tipping happens. And now I want to delve into a bit more theory and how people nowadays think about tipping points. And this is the classical way of explaining this with very simple dynamical system theory. And then if I still have time, I will show how this might be too naive in most systems, but let's not get ahead of ourselves. So what people do is they think we have a system that can be described by a dynamical system. So something that looks like this. The change in this case, your state y, is described by some function that depends on the state itself and some parameter that represents the external forcing that's being applied. So that could be due to the sun in some systems. It could be that people come home and want to turn on their electricity, all sorts of possibilities. And then if you want to have some concrete example in your mind, you might think about this system. So that might help the mathematicians and physicists a bit. If not, just look at pictures. So if you have a system like that, you can make a drawing like here on the right, where again you put on the horizontal axis your parameter that represents the forcing of your system, so that's mu. And on the vertical axis, you put a representation of your states, so y. And then you make a drawing for the lines that represents all the equilibrium states that appear in this system. And then typically you will have, in these systems that exhibit tipping, you would have some sort of shape like this, where there is, in blue, a stable state that represents a certain system state, and in red, another stable state that represents a completely different state of your system. So for instance, if we think about the global climate, this blue line which represents an Earth where there is a lot of ice, and this red line, one where there is not a lot of ice. So then you have this picture, and this is the mental image that most people have when they think about tipping. And then you can say, well, imagine now that we have a certain value for mu and a certain system state such that we're here on this red line. And now if our environmental conditions, if our forcing changes, what then can happen is that mu goes down, and then you follow this red line moving to the left, and your system state changes a bit, but relatively slowly. But then at some point, when you're here, if you continue to decrease your parameter, if the forcing keeps on decreasing, you cannot longer follow this red line, but instead what happens is that you fall off this red line and you end up in the blue line. So that is your critical shift to a completely different state. And this is the classic way that tipping is introduced. However, in systems, there are a few ways in which such critical transitions can appear, and this is one of them. And this is called bifurcation-induced tipping, or B-tipping. And it is organized by crossing a proper tipping point or a proper bifurcation. So that is associated with really crossing a critical threshold that's associated with a critical value of your forcing. However, what is also possible is that your system goes to a completely different state before it crosses the tipping point. So for instance, what could happen is you're here on this red line and you, for some reason, end up in this blue line. And to represent that, you would have to look at the basin of attraction of your equilibria and all that sort of dynamical system, stuff that I didn't want to talk too much about, but have to say here. But basically that means that if you're in this red region, you will go to the red line, and if you're in the blue region, you will go to the blue line, typically. However, there might be some noise that slowly or accumulates. And then over time, it can happen that, well, you're being attracted to this point here, perhaps by some randomness. At some point, your system experiences a large push, such that it passes over this dash line that forms this boundary between this red area and the blue area. And when that happens, you transition from this red line to this blue line. And that's typically called noise tipping. So because it's associated to noise. And then there is another often quoted mechanism that can cause tipping, but that's a bit more complicated, so we'll spend the next slide on that. But before I do, I want to say these are the three most common ones, but there are many other possibilities that don't always have a name or have conflicting names in the literature because some people call it differently. So this third option of rate tipping that is associated with the pace at which your external forcing is changing. So to showcase that, I've brought with me two different of these diagrams. So again, horizontal axis mu, vertical axis is a representation of your space. And in black is, again, here this S-curve, and here this S-curve is skewed. And now what I can do is take a starting point here and then let my parameter mu increase in time. And now in the left case, no matter how fast I change mu, what happens is it will follow all these lines and end up in the upper line always. However, if your system is this more skewed version, what then can happen is if you increase your mu slowly, you do follow this line. But if you force it more rapidly, what can happen is that you do cross this dash line a bit. And because you have crossed this dash line, you do end up in your alternative state. So in this case, it's due to the fastness of your change. So those are the three different elements, the different mechanisms that's possible to cause tipping. Yeah.
Just, I don't know if this is the right moment, but what does it causes it to tilt?
Well, this could be how the diagram looks in your system. I don't know.
But there's no other characteristic in the system that causes it to look like that rather than that.
Not necessarily, no. And if so I didn't show the equation, but basically the difference between this and that is not so much. It's just the tuning of a parameter. But I guess the bottom line of this is you need to know your full global picture to understand this rate dependence. Whereas the others, probably you can go by with local instead. And that also are, say, early warning signs are based off what I think in 2 months, in 2 months people will be talking about it. All right. So that brings me to the end of what I prepared for this classic introduction. And I promise that I will go to a few more complicating factors. And I see I'm speaking for 25 minutes, so I have about 10-ish. Oh, you don't care. So please go on. Please go on. Well, I could go on for an hour, I suppose. So I have 3 different things that could be complicating this picture. One is timescales, one is spatial effects, and the third is when there is heterogeneity in your system. And I'll try to touch upon all of them very quickly to give you a brief overview of what could happen there, but by no means this is everything that could happen. And there might be other sort of situations. This just to showcase that this image that I've painted now is not always the correct one. So to showcase one, and let me now select the second example, skipping the first one. So I have here a very concrete example of a system that's being used to describe interaction between water and vegetation in dryland ecosystems. And if you, the equations don't matter too much now, if you make this diagram with now here A being the forcing parameter and here V being a representation of your state, you can make a diagram that looks like this. And now if you follow the classic ID, what happens is you follow this green line, you fall off and your vegetation dies when there's not enough of, in this case, resource in your system. However, this is all stemming from the fact that in this system there is some feedback. In this case, this UV squared comes from that. And in drylands, this is that the presence of vegetation makes it easier for vegetation to take up water locally, rightly said. But what I can do is make a small change to this model by incorporating explicitly how this feedback works. Because this feedback, how it works is if there's vegetation, the soil changes. And the soil is easier to infiltrate for water. So what I can do is make a small change where I explicitly put this feedback with another variable and put some timescale there. And then if I make a diagram as I did on the previous image, it looks precisely the same. However, if I now do an experiment in which I do change the forcing, so do change the amount of rainfall, so the amount of resource in the system, what can happen now depends a lot on how fast this change is happening. So if this change is happening very slowly, what you will see is that you follow this green line very well. So there you do see this proper crossing of a bifurcation and this tipping with critical shifts. However, if you do change it very rapidly, what now happens is that this feedback cannot keep up. And because this feedback cannot keep up, what happens is that you follow now instead this line. And you don't see any tipping happening anymore. And we've also done the reverse experiment by going back up. And actually, if you do that, you can just go up, following the same trajectory. And what happens under the hood here is that because we have now explicitly made this feedback in our model, what happens is that from a tipping bifurcation, a saddle node bifurcation, we just completely remove that bifurcation and instead end up with what's called a transcritical bifurcation. All the hysteresis is gone, all the tipping is gone. But only in the case that your forcing is fast. So the bottom line for this is if your system has many timescales, as most of our systems do, so there might be stuff happening in the amount of seconds, some things on days, and some things on years. If you do not account for that, you might miss what is happening precisely. So in this case, depending on the timescale of change, very different things can happen.
Little question, Robbin.
Yeah?
Is it as soon as you put the S variable, that's the, I mean, for the right time scale, you get the most critical verification?
Yeah.
Okay.
Yeah. So not in the full system, but in the dynamics that you see. We can talk about the details.
Thank you.
So that's one complicating factor. Another is that all the models that I've shown up till now, and where all this theory has been based upon, is models that do not explicitly take space into account. So these are ordinary differential equations that don't have explicitly a coordinates for space. However, if you, let's skip that one for now. If you look in nature, there are a lot of different systems that have very clear spatial structures. So you have them in mussel beds, in clouds, in savannas, melt ponds, dry lands, and also in other systems. So in animals, you might have spotted that some animals have spots and other kind of patterns. And also in other systems, you might have noticed, for instance, that if you look in this case in America, not everybody is homogeneously spread over the whole continent, but there are certain spots, cities, where people have accumulated. So there must be some spatial structure there that is important. So now the question that you can ask is this important for our mental image that we had? And to model that, you can do the very simplest thing by modeling some spatial effects by diffusion. And then you might think, well, this is sort of similar to the picture we had before, where you have here environmental conditions, you're forcing, here a system state, and this is what our previous mental image looked like. You start with some homogeneous stuff over there, and here's another homogeneous stuff with very different states. And in between, there must be these patterns. However, if you actually do this, and now I will skip the mathematics that is on this slide. If you do this, what you will see is these spatial models do not follow this idea. But instead, what happens is at some point, these uniform spatial states become pattern states. And then you can follow that. And then you have a whole distribution of all sorts of different pattern states that could emerge. And this has consequences on what happens if you're forcing changes. This has consequences on what our mental image should look like. So to illustrate that, oops, yeah, there you go. I've made this slide where I have on the left what our classic tipping image would look like, this same diagram. You fall over a tipping point. If you try to restore it, you have to put in a lot of effort to go across this other tipping point, and only then you do tip. However, if you add these spatial effects, you get a model that looks very different and behaves very differently. So what happens there is if you go down, you follow this red line, you end up here in this balloon full of patterns. There's one pattern selected, then at some point it destabilizes, another pattern gets selected, it destabilizes, another pattern gets selected, and so on and so on. So your degradation in those systems happens more slowly and in more steps, where every time a different spatial structure is selected. And on top of that, if you do the other experiment, trying to restore it or go back to your original state, what now happens is that you can also do that by small increments. This is the green lines here. So in this case, you see that in these spatial systems, these spatial effects could cause your hysteresis to be very different. So you might have smaller hysteresis loop. So in these spatial systems, perhaps your tipping points are not associated always with a full system reorganization. So it might be in part of your domain or just partial shifts. So there's a lot more nuance there, more complexity. So the final thing I wanted to highlight is that what you might see is that your system has some heterogeneity in it. And I think one of the nicest images is actually in one of the earliest papers about tipping, where this picture was, I think, the first figure, and then everybody focused on the right situation, where you do have a similar image as before with proper tipping, and hardly anybody focused on the left situation. And in this left situation, so perhaps I should explain a bit more, but what you see here is a representation of different states. So on the right, what is happening is there's all these red balls representing different elements that build up your system, and all these elements are very similar. And these arrows between them represent that those balls are very well connected. So there's connections between most of the elements that make up your system. And by contrast, here on the left, there's a system where all the elements that make up your system are very different. So that could be, if you're trying to model people, if you do assume everybody is just acting the same, there's no differences, you're more inclined to find behavior that looks like this, whereas in reality, things will behave more like here on the left. And it turns out, if you have a lot of heterogeneity and less connectivity, it's possible that small parts of your system change only. And then you see a similar thing as before, that it's only in part of your system, in part of the elements, that there is a change, but your full system together will change only very slowly. So you see here this critical shift, and here you don't see it, basically. And to stress it a bit more, what you could think about is a spatial system where you have spatial heterogeneity. So what I'm thinking about then typically would be like an Amazon rainforest that's forced by the amount of rainfall, but the rainfall isn't the same over the whole Amazon region, but there is some gradients in there. And what I've done with a very simple model is I've taken the same model, but only changed the precise spatial heterogeneity that I've put there, and then put some forcing on that, and all the same. So the difference between those 6 images is only the spatial heterogeneity that I've put on there. And you see that only because of this, you can get wildly different looking diagrams. And so, for instance, here you will see that if you follow this blue line and fall off of it, you end up in the red line that represents a full system state. But in this one, you end up in this light blue line that represents that only part of your system has changed. And then all the others are variants of that, where it's even much more different. But all to say, if you have spatial heterogeneity, again, your system might behave a bit more nuanced, and you don't have these.
What kind of spatial heterogeneity? Was it larger scale or smaller scale that you look at?
Large scale in this case.
No, but I mean the different pictures.
Yeah.
Was it different heterogeneity?
Yeah,
was it scale difference?
Sorry?
Was it scale difference?
No, it's not. No, it's
Was it all on the same scale,
Yeah.
but just configuration?
Yeah. So that brings me, I think that's a nice time to end, to the summary. So just to reiterate what I said before, basically tipping can happen in many complex systems, and there are different ways that tipping can emerge, for instance, to this crossing of bifurcations, B-tipping, due to noise and crossing of this space and boundary, and tipping, or due to the fastness of your change, R-tipping. And I've also said that typically tipping is fast, abrupt changes, system-wide transitions, leading to an alternative state where there's different workings of your system. And typically there is some irreversibility or hysteresis loop. However, I've also shown you that if you make slight adjustments to our mental image, then things get more complicated, more complex, and more nuanced. So if you want to relook at the slides, look at my website, they're put there. And with that, I'd like to thank you for your attention.
And then we have time for questions.
Yeah.
Maybe it's more of a philosophical question, but what I noticed, so tipping points have become a huge topic in the field of economics. And there's this more and more discussion around positive tipping points. So the idea that we can steer society towards a better state, more sustainable state. And so I was just curious because when I listened to people like Martin Scheffer, they also warn that, and I think that's also what you're saying, but I would like to hear your input on it, is that this focus on tipping points might not be the right thing. It's if we would have a different type of economy that would be more diverse, we would actually see different forms of change rather than these tipping types of change.
Right.
So I was just curious what you think about that.
Yeah, I would think indeed that there you would have a lot of heterogeneity, a lot of other effects, that this simple image of there's just one tipping point and then suddenly everything becomes good.
Yeah.
Better, but that might be a bit too naive. And what you might allude to is that some people like to use all these very simple ideas and try to put it on a very different system. So like
Yeah, or that it both becomes on figuring out the intervention of tipping. So maybe first of all defining what do we agree that is all better, and then how can we get the system that is unhealthy, because we do have an unhealthy ecosystem today. How can we move it over to a healthy system? Whereas maybe, they would be better off focusing on something different, which is the monocultures that we see in our economy. Maybe to make it easier example is maybe, agriculture in the Netherlands. There's a big focus on stikstof, how is it? Nitrogen, which probably is important, right? But there's another thing going on, which is that the system on its own is just a monoculture of things, and also therefore very sensitive to nitrogen.
Yeah.
So just curious what you think about this. Well, if you've ever thought about it, that maybe there's this focus on tipping points, and maybe you have not come across that we wanted to tip it in the right direction. Whereas as science, maybe we should do more to say, well, but if we make the system more resilient and more diverse, actually you don't even see these types of tipping points, not so drastic.
Yeah.
Is that what you're saying? I guess it's
Yeah, I think so.
Okay.
Yeah. Don't fully get what we're trying to say, but it seems the same kind of thing. Yeah.
Well, so if you have a turbid lake, you could say, let's take all the nitrogen out. That's one intervention. Or like he says, we can take all the fish out, but anyway, it doesn't matter, and the other intervention, of course, is to make sure that the lake becomes more diverse, and then you don't get these tipping points so quickly. Yeah,
Precisely. Yeah. You could take it, yeah.
A little reaction on that. Because so when it comes to heterogeneity, there was the part when you see like more heterogeneous avoids tipping point, but like what you showed, for example, for spatial heterogeneity, you see that it's not trivial at all, that it's better, right? I mean, you have situation where heterogeneity leads to a tipping point that's closer to more. I mean, that's what you showed on the.
Yeah.
It's not trivially better to be heterogeneous from the point of view of tipping points.
Where do you show that, just so I understand?
This one is, for instance. So here it's more to the left and there, for instance.
Yeah, definitely.
Yeah.
So the heterogeneity you put in there matters. It's not just diversity, at least, but this is spatial heterogeneity.
Yeah, and it's very simple models again. So it's more complicated. I would think that, like more,
difficult matter.
Yeah.
If you think of a real world system, let's say the society or so, is there any way or any hope you could grasp that with these type of methods? Or is it so complicated that you just have to say, okay, in principle, I know that tipping points might be there, but I have no clue where they are and where they lead to and so on, because things are so complicated and heterogeneous, so much heterogeneity that I cannot really predict what will happen.
Yeah, I would more or less agree with that. So, what I'm also trying to say today is that you see all these nice pictures with just these S curves, and people try to put that everywhere. And I would say it's a bit more nuanced, and things can be more different. So this updated mental image can help you explain or understand what can happen and how you can think about it. But you make great points, right? So we know how things work now. But you know to what different state you would go to, you need to understand how the different state would work, basically, already. So how do you do that? We cannot know. So you make perhaps models like we do with all our complex systems, but then you need to know a bit of the feedbacks that then exist. So that's why complex system size always.
Yeah, so things are only as good as the model in a sense, right? Prediction relies on how well your model captures the essence of what you want to describe.
Yes, and a bit more. That's not only how it is now, but you want to know how it can be.
Well, I mean, to full everything, kind of.
Yeah, yeah.
Yeah, you talked about the complicating factors, spatial effects and heterogeneity, but to what extent are these two really independent? Because what we saw when you talked about spatial effects is that the system state became heterogeneous, right?
Yeah. But this image, for instance, this is talking about more of a network structure where these elements could be modeled like agents, and you have an agent-based model. And there the heterogeneity would be in that there's different agents. Not all agents are the same. So in that way, it's not necessarily the spatial structure.
But these agents have a location in space as well, so you automatically have spatial heterogeneity.
No, not necessarily. If you think about if you think about the internet and how the internet works, then this space is not a relevant factor there. But how things interact and how social media works, that might be an example where there's heterogeneity and space is not that important. But I would agree in general, everything is just mixed together, and everything together is important, yeah.
I have a question. You used the upcoming phone, a mobile phone, as a tipping point. That's sort of the adoption of the mobile phone. But I was wondering, aren't there then also more layers of tipping points, because the adoption of the mobile phone changes the way we connect, or you could say everybody's going to use the phone, so there's the tipping point. But we also get then the smartphone, that's a tipping point in the way we are thinking, or maybe less thinking. There's a tipping point in our cognition, but they're not evenly aligned. It's based on more technology. So that's the mobile phone is a tipping point, which sort of led to multiple tipping points on different focus areas or different systems defined by the.
I guess so. Yeah. So it's good.
Cascading effect to where we are now, and now we're trying to, because I saw you how you try to go back in after tipping point. What we do now see at schools, that they're just taking the phones away from students and learners to get back to already a part of what we've lost through the phone.
Yeah.
I think we would have the Nokia based,
They celebrate like the 20th birthday. I hope it isn't. But this cartoon was even before that, like just being available all the time. People are also questioning sometimes, right?
Yeah. It has many tipping points. So on technological level, on cognitive level, on social level, on how we interact. So there's and they are not aligned. That's so interesting, because the technology evolves, and that will induce more different tipping points.
Yeah, so with this, and they call it the diffusion of innovation.
Yeah.
What they really think about is how a new technology would become widespread.
Yeah.
And then to isolate that, they think there needs to be a critical mass, and then at some point everybody.
Yeah.
And then yeah. What you were saying would be what happens afterwards. Would by this change in different kind of systems.
Based on new technology,
Yeah.
because
Yeah.
first the Nokia, there was already a change, and then we have the smartphone. That's kind of a big change on even our mental health.
Mhm.
And
Yeah.
so in our society. So yeah. Interesting.
Sora. Yeah.
Yeah, you started at the beginning with the cast model, and then the cast model, there's this one variable which basically governs like if you have this hysteresis effect or if you have like a gradual effect. So it's basically on the, I guess, y-axis. And then I wanted to
This one, you mean, right?
no, the actual cast model, like the 3D cast model.
The thing. This thing.
Yeah,
Yeah.
so basically on the, I guess, y-axis maybe, there's this effect which governs like if you have this gradual like effect on the like, behind part of the model, or if you have the hysteresis effect on the like front.
Yeah.
And I wanted to ask if you would say that the spatial heterogeneity and so on would be like basically this variable in the cast model, or if this is like an additional external effect.
I would say this picture is just wrong for those systems.
Okay.
Because it's and also this landscape that works only in systems where basically there's conservation of something, and that's not the case typically.
Mhm.
So it needs conservation of energy or conservation of something for this to be the full picture. So mathematically speaking, you need to have the diagonal function, and your function looks like this, and most systems do not look like this. That's basically it. And then, well, if you want to make your mental image based on this, then I would say it's not possible.
Interesting. Okay. Thanks.
So that's why these bifurcation diagrams, those are more universally applicable.
Mhm.
But then if you want, you can think about this spatial stuff means that what happens is it folds this thing into multiple folds. So it's fold and fold and fold, and they're all small folds happening after each other. That's more of how I would imagine that.
Okay, so basically more of changing the
Yeah.
shape of the hysteresis than actually like explaining this
Yeah.
carbon this.
Yeah.
Basically, yeah. Okay, right to this change. Okay, thanks.
Oh, yeah, she says yes. Yeah.
So one thing I've been also trying to think through is whether this also has to do with our notion of stability versus instability in what we think, well, reality is ideally. And so if you have indeed, well, and that's why I think this image, I know it's not correct that you're saying, right? But what I always say when I teach this is that in this case, you do have a stable system because it simply can't go anywhere. Whereas if you have this, you have more of a chance of having an unstable system.
Mm-hmm.
But we have been told, and even you speak a bit like that we always talk about stable systems, right? That the system goes towards stability, whereas we actually know that most ecosystems are not in constant states of stability. Their healthy systems are usually in states of some instability, extreme instability, some. So I was just curious whether how that fits into your story, the story of stability versus instability.
I would say that this is the difference between having a proper fixed point where everything is really stationary in time, but you could have a system that is stable in a periodic state. So there might be periodicity, or it might be chaotic effects happening there. And those states could be stable as well. So then what people do is just put this mental image of this picture or of these diagrams, and then think these lines do not represent precisely a state where everything is just stationary, but it could be a chaotic state. Or I should say there might be some forcings, and because of that, there might be some fluctuations. That is your stable state. And then that picture largely works, but then there are many additional, more complicating factors, but those typically tend to be on the more mathematically interesting sides. And I thought for this audience would be good. But in general, this picture would just generalize to those systems. So then you would say like, let's go back to this picture here. This does not represent one particular state possibility, but a collection of them that represents some chaotic stuff that can happen.
Okay.
Yeah.
So really, the instability does not have an effect on the discourse.
Yeah.
Okay.
And then things get more complicated, but that's yeah.
I think we're gonna leave it there. It's getting close to 1, so let's thank Robbin again.